Welcome back, scholars. Today we're going to dive deeper into matrices and specifically look at how to find the inverse of a matrix and how that can be used in further matrix applications. Let's get started by defining what it means to be an inverse of a given matrix. Well, by definition, a matrix and its inverse, when multiplied, give the identity matrix. We saw previously that an identity matrix is a square matrix with ones along the main diagonal and zeros for the remaining entries. When we think about a matrix and its inverse, the relationship is analogous to that of a real number and its reciprocal. Recall that reciprocals, by definition, multiply to give 1. You may also recall the use of the -1 exponent. That means take the reciprocal of the base. The notation for an inverse matrix is also the -1 exponent, with the base referring to the matrix we are taking the inverse of. For example, a to the -1st power means take the inverse of matrix A. The determinant is used to decide or determine if an inverse matrix exists. In general, if the determinant of a given matrix is not equal to 0, then the inverse matrix does exist. We will look at two different ways to find the inverse of a given matrix, starting with using linear equations. In this example, we're asked to find the inverse of A if it exists. Well, remember, by definition, A times its inverse, which we've denoted as this square matrix with entries W, X, Y, and Z, will be the 2x2 identity matrix. We'll start by simplifying the left side of the equation, multiplying A and the inverse of A. Remember that when multiplying matrices, we go row by column and then add the products. So this would be 2 times W and 1 times Y, then 2 times X and 1 times Z. Bottom row, we have 3 times W and 0 times Y. Then last column, we have 3 times X and 0 times Z. Our simplified expressions will look like this. For now, I've kept the coefficients 0 and 1 so that we can clearly see the result of multiplying the two matrices on the left side of the equation. Alright, if you think way back to our first lesson, we talked about equal matrices, and that's exactly what we have here. We have two matrices that, while they look different, are actually equal. So we can set each corresponding entry equal to one another. For example, 2W plus 1Y equals 1, and so on. When we do this for all four entries, we end up with a system of 4 linear equations, which I've shown below here. Now, to find the values of W, X, Y, and Z, those are the entries in our inverse matrix, I'm just going to solve each equation. Very simple. I have W equals 0, X equals 1/3, Y equals 1, and Z equals -2/3. Now we'll place those values into their appropriate locations on the inverse matrix. And we've done it. We found our first inverse matrix. Now there is another approach that we could use, which involves using a formula. This formula can be derived using a system of equations like what we just did. But in general, we see that the inverse of a given matrix, again, that's denoted with the -1 exponent, can be found by using the reciprocal of the determinant as a scalar, and then by applying a few adjustments to the original matrix itself. Note here that A and D have swapped positions. Also, C and B have had their signs reversed. This next example says find the inverse of B if it exists. To use this approach, we'll start by finding the determinant of B. Remember, that's AD minus BC. For this matrix, that will be 4 times 2 minus 1 times -1. So that will be 8 plus 1, or 9. Next, we'll swap the entries A and D in our 2x2 matrix, and we'll reverse the signs for C and B. Now we apply our scalar multiplication, which is just like using the distributive property. Every entry in the matrix gets multiplied by 1/9. Our final matrix will be 2/9, -1/9, 1/9, and 4/9. To verify that we've done this correctly, we could multiply B and B inverse to check to see that we have a 2x2 identity matrix. Last, we want to look at how we can solve some simple matrix equations using inverses. In the real number world, we see equations all the time. For example, if we have A times X equals B, to solve for X, we would just divide both sides of the equation by A. In the world of matrices, we effectively do the same thing. Instead of dividing, we multiply by the reciprocal, which is the inverse matrix in this situation. A quick note, be careful here because B times A inverse is not the same as A inverse times B. Remember that matrix multiplication is not commutative. We will want to use A inverse times B in this case. I'm going to walk you through two solved examples. First, let's look on the left. I want to solve for matrix X. To do this, I need to multiply both sides of the equation by the inverse of this leftmost matrix. I will start by finding the determinant of that matrix. 1 times 7 minus 1 times 6, that'll be 7 minus 6, which is 1. That's convenient. Next, I'm going to swap entries A and D and reverse the signs of entries B and C. Then multiply by the reciprocal of the determinant as a scalar. That'll be 1 over 1. This will yield the inverse matrix with entries 7, -1, -6, and 1. Now I'm going to multiply that by the right-hand matrix in our equation. Remember that order matters. The inverse matrix will come first. We'll multiply row by column and add our products for a final result. Matrix X is given by the 2 by 2 matrix with entries 13, 17, -11, and -14. Looking on the right, we have the same situation. I want to define matrix X. To do this, I need to multiply both sides of the equation by the inverse of this matrix on the far left. We'll start by finding the determinant. That'll be 3 times 3 minus 1 times 6, or 9 minus 6, which is 3. Next, we will use the reciprocal of the determinant as a scalar. That's 1 over 3. And I'm going to swap the entries A and D in my original matrix and reverse the signs of B and C. Our inverse matrix will have the entries 1, -1/3, -2, and 1. Next, we multiply both sides of the equation by that inverse matrix. On the left, we have just the identity matrix and X remaining. Remember that the identity matrix behaves like a 1, so we can simplify the left-hand side of the equation to just X. On the right-hand side, I have the inverse matrix times this 2 by 3 matrix. These dimensions are compatible for multiplication, so I'll go row by column and add my products. Simplified, I end up with matrix X given by the entries -1, 4, -3, and then along the bottom row, 4, -8, and 7.